In this video, I'm going to use the method of OLS to find an expression for beta 1 hat. I've already discussed these equations with you. So this is a sample equation. Using this sample equation, we can write this mathematical expression for ui hat. And using this mathematical expression for ui hat, we can write a mathematical expression for summation of ui hat square, which is this. Now, as per the method of OLS, we have to choose beta 1 hat and beta 2 hat such that summation of ui hat square is minimized. That means our focus is on minimizing this particular expression. As I told you earlier, we are going to do this minimization exercise given a particular sample. So for the visualization purpose, I have also written a demo sample over here. In this demo sample, I have taken n values of x and n values of y. Note that as this exercise is going to be a general exercise, so I'm not writing any particular values of x and y over here. We are going to work with the notation x1, y1, x2, y2 and so on. So over here, x1 denotes the first value of x and y1 denotes the first value of y and so on. Consequently, the sample size is n. So because the x can take n values and y can take n values, the sample size is n. So this is the demo sample that I'm going to use for visualization purpose in this exercise. Now, as I told you in my last video, we have to partially differentiate summation of ui hat square with respect to beta 1 hat. So that means we have to differentiate this expression. Now, as you can see, this particular expression has a summation sign over here, and many students do not feel that much comfortable with the differentiation when there is a summation sign involved. So I'm going to show you this differentiation exercise using two methods. In the first method, I'm going to expand the summation and then I will do partial differentiation term by term. In the second method, I will not expand the summation and I will do the partial differentiation directly. My advice would be that you should not rush this video and you should take a look at both the methods because you're going to learn something from both of these methods. So let's get started with the method number 1, which I'm going to write as M1. Now, before I expand the summation, I want you to note one thing over here. This summation that you see over here, this is going from I equal to 1 to n. Okay, so this is going from I equal to 1 to n, and it is going till n because our sample size is n. If I change the sample and if I take a sample which has a sample size of 5, then the I will range from 1 to 5. Okay, and the entire exercise that I'm going to do in this video, I will be writing the summation sign a lot. Whenever I write the summation sign, that would mean that I is going from 1 to n. I'm not going to write I going from 1 to n again and again just for the sake of some convenience in writing. Okay. So in method number 1, we are going to expand the summation sign. So that means we can write summation I equal to 1 to n ui hat square is equal to y1 minus beta 1 hat minus beta 2 hat x1 whole square plus y2 minus beta 1 hat minus beta 2 hat x2 whole square, and this is going on till yn minus beta 1 hat minus beta 2 hat xn whole square. So because the summation was ranging from I equal to 1 to n, the first term that we have over here is y1, then we have y2, and this is going on till yn. The second term is minus beta 1 hat. Note that the beta 1 hat does not have any I element, so it remains minus beta 1 hat in the first bracket, it is minus beta 1 hat in the second bracket, and even in the last bracket it remains minus beta 1 hat. The third term is minus beta 2 hat, and this is multiplied by a x variable. Now x does have the I element, so the x values are going to range from x1, x2 till xn, and beta 2 hat does not have an I element, so beta 2 hat is going to remain as it is. So over here in the first bracket you have beta 2 hat, in the second bracket also you have beta 2 hat, and in the last bracket also you have beta 2 hat. Okay, so this is the expansion of the summation sign. Now we have to partially differentiate summation of ui hat square with respect to beta 1 hat. So now we are going to do this partial differentiation exercise term by term. So let's differentiate this term first. So as per the rules of the partial differentiation, this will become 2 multiplied by y1 minus beta 1 hat minus beta 2 hat x1 multiplied by 0 minus 1 minus 0. So this term over here is the partial differentiation of this first term with respect to beta 1 hat. Let me try to provide you some intuition regarding this partial differentiation exercise that I have done. So over here we have a term inside the bracket and then we have a square. So you have a 2 over here. When you do the partial differentiation of this term with respect to beta 1 hat, this 2 will come over here and then this will be multiplied with the term that was inside the bracket. Okay, and this second term that you see over here, this is because of the chain rule. So we get this term because we partially differentiate the term that was inside the bracket, that is y1 minus beta 1 hat minus beta 2 hat x1 with respect to beta 1 hat. Okay, so this 0 minus 1 minus 0 that I have written, this is actually the partial differentiation of the term that was inside the bracket, okay, with respect to beta 1 hat. Note that y1 over here is a particular constant. As you can see, y1 is the first value of y that we have in the sample, and when you differentiate a particular constant, you just get 0 in return. So that's why we have 0 over here. The second term is minus beta 1 hat. When you differentiate minus beta 1 hat with respect to beta 1 hat, you're going to get minus 1. So that is over here. The third term is minus beta 2 hat multiplied by x1. Now note that we are doing a partial differentiation exercise with respect to beta 1 hat. So we are going to treat beta 2 hat as a particular constant. So beta 2 hat over here is a constant, and even x1 is a constant because x1 is the first value of x, as you can see in this demo sample over here. So this implies that beta 2 hat multiplied by x1 is a constant, and when you differentiate a constant, you get 0 in return, which explains this minus 0. Okay, so this is how I have done this differentiation exercise. Now similarly, we can differentiate the second term, the third term, and so on. So let me create some space to show you that differentiation. So now if I differentiate the second term, that is this term, with respect to beta 1 hat, I will get 2 multiplied by the term that is inside the bracket, which is y2 minus beta 1 hat minus beta 2 hat x2. And then using the chain rule, now we are going to differentiate this term that is inside the bracket with respect to beta 1 hat. If you differentiate y2 with respect to beta 1 hat, you're going to get 0. Because y2 is a particular constant, it is actually the second value of y in our demo sample, and when you differentiate a constant, you get 0. The differentiation of minus beta 1 hat with respect to beta 1 hat is going to be minus 1, and the differentiation of minus beta 2 hat x2 with respect to beta 1 hat is going to be 0. Similarly, we can do this for the nth term. For this particular term, we will have 2 multiplied by yn minus beta 1 hat minus beta 2 hat xn, and once again using chain rule, we will have 0 minus 1 minus 0 over here. So let me try to write this in a neater manner now. So when we partially differentiated summation of ui hat square with respect to beta 1 hat, we got that this is equal to 2 y1 minus beta 1 hat minus beta 2 hat x1, and this was multiplied with 0 minus 1 minus 0, which is nothing but minus 1. When we differentiated the second term, we got 2 y2 minus beta 1 hat minus beta 2 hat x2. This is beta 2 hat x2 minus 1. And when we differentiated the last term, we got 2 yn minus beta 1 hat minus beta 2 hat xn minus 1. So this 2 multiplied by minus 1 becomes minus 2. Similarly over here we have 2n minus 1. So this also becomes minus 2. Over here we have 2n minus 1. So this also becomes minus 2. So basically in every term that we have over here there is minus 2. So I can take minus 2 common. And now I'll be left with y1 minus beta 1 hat minus beta 2 hat x1 plus y2 minus beta 1 hat minus beta 2 hat x2 plus, and this is going on till yn minus beta 1 hat minus beta 2 hat xn. Now we can write these y terms together. So we have y1 plus y2, and this is going on till plus yn. So I can write this is equal to minus 2, and I can club these y terms together and write them in a single bracket. So we can write y1 plus y2 plus going on till yn. Similarly, as you can see over here, in this bracket I have minus beta 1 hat, in this bracket I have minus beta 1 hat, and in the last bracket also I have minus beta 1 hat. In total there are n brackets, so that means we are adding minus beta 1 hat n times, and if you add a constant n times, it becomes that constant multiplied by n. So if you add minus beta 1 hat n times, it will become minus n beta 1 hat. Okay. Now over here it is minus beta 2 hat x1 minus beta 2 hat x2, and this is going on till minus beta 2 hat xn. So I can actually take minus beta 2 hat common, and within brackets I can write x1 plus x2 going on till xn. Okay, and this is equal to minus 2. This can be written as summation of yi, where I is going from 1 to n, minus n beta 1 hat minus beta 2 hat, and this can be written as summation of xi, where I is going from 1 to n, and this is the partial differentiation of summation of ui hat square with respect to beta 1 hat using the method number 1. So this is the end of step number 1 using the method number 1. Now I'm going to show you the same step using the method number 2. In the method number 2, I'm not going to expand the summation sign, I'm just going to differentiate it directly. So let me create some space for method number 2. So method number 2, summation of ui hat square is equal to summation yi minus beta 1 hat minus beta 2 hat xi whole square, and now we are going to partially differentiate this with respect to beta 1 hat, and I'm not going to expand the summation sign. Now it is going to work in the same manner. So we have a 2 over here, so when you do the differentiation, this 2 will come over here, then this will remain as it is. So we will have 2 summation yi minus beta 1 hat minus beta 2 hat xi, and now using chain rule you have to multiply this with the differentiation of the term that is inside the bracket, that is this term. Okay, this term. As I told you in method number 1, yi is representing the y values that we have in our sample data. So when you differentiate this with respect to beta 1 hat, you're going to get 0. The differentiation of minus beta 1 hat will become minus 1, and the differentiation of minus beta 2 hat xi, this will also become 0. Okay, this second term is 0 minus 1 minus 0, so basically this is nothing but minus 1, and if you multiply minus 1 by 2 you get minus 2. So this is minus 2 summation yi minus beta 1 hat minus beta 2 hat xi. Now see, we have a summation sign over here which is going from I equal to 1 to n, and there are 3 terms in this bracket. So now we are going to apply this summation sign on these 3 terms one by one. Okay, so this is equal to minus 2 summation of yi minus summation of beta 1 hat minus summation of beta 2 hat xi. Now note that this is not the final expression. There is one last thing that you need to do over here. So this is equal to minus 2. Now let's see if summation of yi as an expression makes sense, or do we need to do some changes over here. So once again, try to visualize the demo sample that we had. So we have data on 2 variables, and the x values are ranging from x1, x2 till xn, and the y values are ranging from y1, y2 till yn. So this summation yi, where the summation is going from I equal to 1 to n, this means the sum of all these terms. Okay, so summation of yi as an expression is making sense. Summation of yi means that we are summing all the y values that we have in our sample data. So no need to change this. We can just keep it as summation of yi. This is a sensible expression. Now let's talk about summation of beta 1 hat. Note that we are doing this exercise for a particular sample, and when you do the minimization exercise for a particular sample, you're going to get only one line of best fit. That means beta 1 hat is a particular constant. And when you sum a constant n times, you can write n multiplied by that constant. So instead of writing summation of beta 1 hat, I'm going to write n multiplied by beta 1 hat. Okay, so this is a more sensible way of writing it. Minus, let's discuss this term now. Many students do mistake in writing this term. They think that if we apply summation on a constant multiplied by a variable, then it is going to become n beta 2 hat summation xi. Well, this is absolutely wrong. Okay, it will not be n beta 2 hat summation xi. It will just be beta 2 hat summation xi. Let me show you why am I saying this and how can you visualize this. So over here we have summation of beta 2 hat xi. Try to expand it. If you try to expand it, you will see that it is equal to beta 2 hat x1 plus beta 2 hat x2 plus beta 2 hat x3 going on till beta 2 hat xn. So this particular expression over here, if you try to expand it, it will look something like this. Okay, now as you can see, beta 2 hat is common in every term. So if you take beta 2 hat as common, you'll be left with x1 plus x2, and this is going on till xn. So this is equal to beta 2 hat summation xi. So that means if you have a summation on this term, it is not equal to this, it is equal to this. So instead of that term, I can write beta 2 hat summation of xi. Okay, so what is it that we have learned while coming from this expression to this expression? Basically, if you apply summation on a standalone constant, so beta 1 hat is a standalone constant. By standalone constant, I mean it is not multiplied by any variable. So when you apply a summation on a standalone constant, you can write it as n multiplied by that constant. However, if the constant, that is beta 2 hat, is multiplied by a variable, so this is not a standalone constant, beta 2 hat is multiplied by a variable, then if you apply summation on this term, then the summation is going to skip the constant and the summation will only be applied on the variable, and you will not write anything like n. Okay, so if you try to do this, then beta 2 hat will come out and the summation will only be applied on xi, and summation of xi means that you are just summing up these x values that you have over here in the sample data. Okay, so I hope this much is clear. This was your method number 2, which is actually a shorter method as compared to method number 1. So when we worked with method number 1, we got this equation. When we worked with method number 2, we got this equation. You can check that both of these equations are exactly same. Okay, so it doesn't really matter which method you work with. From your exam perspective, you can actually work with method number 2 as this is short as compared to method number 1. Okay, so this is all about step 1. So basically from step number 1, we have got this equation. Okay, now let's proceed to step number 2. In step number 2, we have to put the partial differentiation equal to 0, and then we have to solve for the expression of beta 1 hat. So the result that we have got for the partial differentiation is this. So now we are going to put that equal to 0. So this implies minus 2 summation of yi minus n beta 1 hat minus beta 2 hat summation of xi is equal to 0. Now we are going to solve this expression for beta 1 hat. So to do that, I can divide both the sides by minus 2. So this and this gets cancelled, and 0 divided by minus 2 is just 0. So this implies summation of yi minus n beta 1 hat minus beta 2 hat summation of xi is equal to 0. Now because we are doing this partial differentiation exercise with respect to beta 1 hat, so we are going to solve this expression for beta 1 hat. So this implies that summation of yi minus beta 2 hat xi, I can take this to the right hand side over here. So this is equal to n beta 1 hat. And this implies that beta 1 hat is equal to summation of yi divided by n minus beta 2 hat summation of xi divided by n. Now try to imagine that what is this summation of yi divided by n. So basically once again in your sample data, you had values from x1 to xn and y1 to yn. So y1, y2 till yn. So summation of yi means the sum of all of these y values, and if you divide by n, which is the sample size, that means you are finding the sample mean of y values. So instead of this summation of yi divided by n, I can write y bar, which is actually the notation for the sample mean of y, minus beta 2 hat. Similarly, this term that you see over here, in this term in the numerator we have the sum of all the x values. That means the sum of all of these values, and then this is divided by the sample size. So this is the sample mean of x, and the notation that we have for the sample mean of x is x bar. Okay, so this implies that beta 1 hat is equal to y bar minus beta 2 hat x bar. So this is the formula that we get for beta 1 hat when we use the method of OLS. Now note one thing over here. To find the value of beta 1 hat, you first need to know the value of beta 2 hat. You cannot find the value of beta 1 hat without solving for beta 2 hat first. So whenever you get some kind of question in the exam where they give you some data and ask you to find the value of beta 1 hat and beta 2 hat, then you should always first solve for the value of beta 2 hat because that will be utilized to find the value of beta 1 hat. Okay, so this is the formula that we have for beta 1 hat, and this marks the end of your step number 2. As I told you in my last video, there is also a step number 3 which is completely optional. However, for the sake of completion, let me show you that step as well. So in step number 3, which is an optional step, so this is optional, we have to check the sign of the double derivative of summation of ui hat square with respect to beta 1 hat. Okay, so when we partially differentiated summation of ui hat square with respect to beta 1 hat, we got that this is equal to minus 2 summation yi minus n beta 1 hat minus beta 2 hat summation xi. This is something that we got in step number 1. Now we have to differentiate this again with respect to beta 1 hat. So if I differentiate this again with respect to beta 1 hat, then I will get minus 2. The differentiation of summation of yi is going to be 0, and this should be quite easy to understand. Once again, take a look at the sample data. In the sample data, you have y values going from y1 to yn and x values going from x1 to xn. If you are given a particular sample, then the summation of yi means the sum of all of these y values, which is going to be a particular number. And when you differentiate a constant, you get 0. So this is 0. This is minus n. The differentiation of beta 1 hat with respect to beta 1 hat is going to be 1. Minus, similarly, this term is also 0 because beta 2 hat is a constant and summation of xi is also a constant. It is just the sum of all of these x values when you are given a particular sample. So a constant multiplied by a constant gives you a constant, and when you differentiate a constant, you get 0. So this is equal to minus 2 multiplied by minus n, which is equal to 2n, which is definitely greater than 0 because n is your sample size and sample size cannot be negative. So 2n is definitely greater than 0. That means the expression that we have found for beta 1 hat is indeed minimizing summation of ui hat square and not maximizing. Okay, so this is all for this video. The purpose of this video was to get this formula for beta 1 hat. Now in the next video, we are going to solve for beta 2 hat.